All right, for problem 12, it says the points 1, -1 and 1, -5 are on the graph of a function defined as y equals f of x that satisfies the differential equation dy dx is equal to x squared plus y, which the following must be true, and they're asking questions about local minima, maxima, and points of inflection. So there are different ways to do this problem. I'm just going to explain my way. There's a first derivative test way where you do interval testing, but for this problem, because the way dy dx was defined, I wouldn't feel comfortable doing that. So you're going to see me use the second derivative test. So let's review the concept with that, okay? So let's first think about, what does the first derivative tell you? So if your first derivative is positive, that means your function is increasing. If your first derivative is negative, it means your function is decreasing. If your first derivative is 0, it means that at that moment your your function is constant. And so we use the first derivative in a sense like this because it can help us find all three in a way. So if you have a maximum point, your derivative would be 0. If you have a minimum point, your derivative would be 0. And then also if you have an inflection point, remember an inflection point is where your graph changes from concave down to concave up or the other way around. And notice that your derivative is 0 is there as well. So one thing you need to know is if your first derivative isn't 0, you're not going to have a maximum, a minimum, or an inflection point, okay? And then next, you should know if your first derivative is 0, you shouldn't assume that you have any single of these three. You'd have to figure, you have to look into it a little more. But you could use the second derivative to figure out which one's which. Because if your second derivative is negative, that means your graph is concave down. And so if you've got first derivative 0, second derivative negative, you've got a maximum. If you've got, at a minimum, you'd have concave up, which would be second derivative positive, and then you'd have first derivative 0. At an inflection point, your first derivative would be 0, and your second derivative would be 0. So hopefully that part makes sense. Okay, now let's get started. So let's figure out what's dy dx at the point -1, -1. You just plug in -1 for x and -1 for y, and you would get 0. So now let's go ahead just to make sure we get everything done here. So let's do dy dx at the other point, 1, -5. So plugging in 1 for x and -5 for y gives you something that isn't 0. And I honestly don't even care what it is. I think it's -4, but the point is that it isn't 0. And so we shouldn't expect that at the point 1, -5, we'd have any of these things since your first derivative was not 0. Okay, so what that would do is it could just rule out a and b right away. Hopefully that makes sense. Okay, so now let's look at dy dx. Since your slope is 0, let's figure out which of these three pictures we've got by using the second derivative. Oops. And using correct notation when you do it. Okay, so we're going to figure out, let's get a rule for the second derivative, and then we'll worry about plugging the point in. So the rule first. We're taking ddx of both sides of this. Here, I'll even show it real quick. We're doing ddx of this, and we're doing ddx of this. So ddx of x squared would be 2x, but ddx of y would be dy dx. So it's up to you. You could take x squared plus y and replace it you could put x squared plus y in right there. I'm not going to because there's another way to get your answer. So we're looking for what's the second derivative at the point -1, -1. So we'd put in -1 for x, so we'd have 2 times -1. And then dy dx at that point -1, -1 was 0. So I'll just put the 0 in there. And then you end up with -2, and since it's negative, that means at this point you've got concave down behavior, and then you already found out the derivative was 0. So you've got a maximum. So the answer, my friends, is C. Hope that makes sense.